Good morning to all of you. So yesterday we had discussed this how this signal is generated in a pulse NMR setup. So I told you the conversion, the giving example of first I gave you an example of simple how does this was the aspect, this image, the GIF image tells you about how the things operate. You have B0 and B1. B1 is the part of uh, magnetic field vector of the radio frequency that comes in as green color. So and the blue one is the B0, the static magnetic field. Okay, so precessional motion around the static magnetic field, that's what you are seeing. Then when there is a circularly polarized radio wave, so when we move to the change the frame of reference, we find that B1 is static, so is M, the magnetization vector, and it starts precessing around B1, the green that appears after a while. Okay, so this is the basic idea that what happens, it starts precessing, and this precession is exactly the depending on the length scale of the length of the pulse, I mean the time duration of the pulse. So we call it like pi by 2 pulse, pi pulse, like 90-degree pulse or 180-degree pulse, depending on how much this red vector is tipping from the top to bottom, entirely reversing its direction, or it is just in the midway, lying midway from the, so that duration can be calculated, and you can have a, so that is pi by 2 into gyromagnetic ratio, and then the B1, the field. So that is the duration of the pulse you can define. So depending on the requirement, we can have different durations of pulses, and mostly we call them as 90-degree pulse or 180-degree pulse. So in a 180-degree pulse, what will happen, that this circle, it will move here, so the direction will be completely reversed. So in a 90-degree pulse, it is easy to imagine that uh, the population of alpha and beta spins are all equal. In a 180-degree pulse, when it is applied, that means the magnetization vector, which is summation of all these small angular momenta, is most of them are now pointing in this direction, the reverse direction. So that is 180-degree pulse, what it means. So this is these are the things that will be that we discussed yesterday, and then we again come out of this rotating frame of reference and become an observer in the lab and place a coil where the signals from this decay of the magnetization vector, the relaxation of the magnetization, there will be there's a signal that will be induced in the coil, which you can detect and get a spectrum on the reference. So to get that spectrum, you have to actually process the signal, and signal processing happens through, so actually if it is only one nucleus, sorry, it is only, if you have, then you will get this kind of signal. For one nucleus you will get, if you have a one nucleus, I mean only one type in a molecule, then possibly this kind of signal. So exponential decay profile you can see very clearly happening over there. The pulse induces is when it is absorbed by the single this nucleus, and then it starts oscillating. Once the pulse is gone, it starts decaying in this manner. So this is what we talk about. So this happens because there is relaxation of the spins, so when we say that magnetization vector shrinks exponentially with time, so we are actually talking about you have a huge value of magnetization. Now it goes on decreasing, and finally it is very so small that, so this is the vector m which goes on decreasing in magnitude, because so that will happen when some of them are now changing in from alpha to beta, and so the net magnetization decreases. If all the if you have 100 of nuclei present in the sample, all are pointing in one direction, the m will be highest, okay, the magnetization vector. If some of them are now pointing in the other direction or in the opposite direction, you will have some decrease gradually. So that is what we are talking about. This is, so something like that happens. The spins which were having suppose the z component as plus half, now some of them will have, there will be a change, relax, they will relax, because ये excitation था, it was a excitation of the spin states. Now they will relax back, and so spin state will change. And how it will change, that's what we were trying to learn, and in that context we get that relaxation dynamics, the spin relaxation terminology comes in. So one of the relaxation of the, if you, so what we were looking at is the y component. So it was the xy plane in which the b1 vector was rotating. The radio frequency wave का, radio frequency जो wave थी, रेडियो वेव का जो b1 वेक्टर था, मैग्नेटिक फील्ड वेक्टर, वो एक्स वाई प्लेन में था। मैंने बताया था आपको, z वाले प्लेन में क्या था, b नॉट था, राइट। सो इट इज द y component of the magnetization vector which is undergoing a change as as soon as the pulse is removed, the decay starts. Like this happens. So that is given by that equation that I told you, t by t2, and yesterday I told you that if you place t is equal to 0, you will get the maximum value of the magnetization, and then if you, as the time increases the decay, you will see the decay. So you can also define t2 when t is equal to t2, you can define it as the, it is 1 by e times of the value original thing. And so so magnetization so this was the case of a simple thing. Then we discussed that if you have ax2 nuclei connected to each other through chemical bond in a molecule, something like that, then the signal will be, of course it will be the pulse that you are getting in the coil, oscillating signal in the coil, that will have a something like this. And as this number of nuclei, magnetically active nuclei connected through chemical bonds increases, then this signal will get more and more complicated. This signal is typically called FID. Uh, so FID curve, and you need to mathematical help. You need to take algorithm, make an algorithm, a program, feed into the system computer, which will convert this signal into usual thing, that normal thing that you need for your analysis in organic or inorganic chemistry, that at what frequency signal appears and what is the intensity. So intensity versus frequency, or the, if you know the frequency, you know normally then you can calculate the chemical shift values del. So all these things, so that is frequency domain thing. So you obtain it for by deconvoluting this spectrum, this signal. So that conversion from a time domain to frequency domain is done through Fourier transformation. So that is, so we went to the example of this ethanol again. So this is a typical FID curve obtained in a pulsed NMR, which when transformed through using Fourier mathematical this framework, then we get this kind of signal. So why it was complicated, So this FID curve was looking complicated because it has 8 different signals, 8 different Larmor frequencies for corresponding to you see 3 here, 4 here, 1. So 4 plus 3 plus 1, 8 different Larmor frequencies are present in that sample. So corresponding to each of them you have uh, oscillations, and so the the pulse that you are getting, the pulse profile that you are getting finally is a complicated one, looks very complicated, and then it is, yeah, with the help of algorithm you can change it and get it. So now we come back. So this decay that you observe is happening because the spins are now changing, the spin states are changing, the orientation or something is of the spin angular momentum vector is undergoing a change, and that gives rise to that kind of, so how it changes, that's what we are going to learn. So 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 uh, so magnetization vector in the xy, so we are focusing on the xy plane now, that when once the radio frequency is gone, there is v1 is gone, there's no so when v1 is gone, then the effect that precession that we have additional precession that will also be not there, and slowly that you will see that that component of y starts decaying. So in absence of that radio frequency, nuclear spins were uh, the z component was along the sorry, the magnetization vector was along z, so there will be a tendency to return back to that situation. Okay, so that is called spin relaxation. So that was the normal situation when you had a static field b naught in absence of radio frequency. So that is what they will try to get back to, that thermal equilibrium situation, kind of situation, once the pulse is gone. So that thermal distribution of like if you have 100 nuclei present in a 1 gram of sample, say something like that, then you can each, so population of each spin state can be described by Boltzmann distribution for the alpha state and beta state, beta spin state. Now magnetization vector, so suppose if 90-degree pulse is applied, um, sorry, the 90-degree pulse, as I told you, is means that you have equal number of alpha and beta spins in the sample. If you say, so this was the terminology that I told you earlier, to keep in this mind, we will be using this often while discussing pulse. So 180-degree pulse, so I think that I discussed all things, that visualization is that the complete flipping of the net magnetization vector complete in the z direction, so it becomes totally opposed to what it was initially, like that. So 180-degree pulse means you are inverting the entire population. जो पहले जितना अगर 100 के 100 ऊपर की ओर पॉइंट कर रहे थे, उनका z कंपोनेंट प्लस हाफ था, अब सारा का सारा माइनस हाफ हो जाएगा. So that is 180-degree pulse. So that will also mean that you have more of beta spins. If 180-degree pulse is applied, you have more of beta spins than alpha spins. Okay, if you apply 90-degree pulse, then both alpha and beta spin states are equal in population, in terms of population. So after the pulse is gone, yes, they will revert back to the thermal equilibrium situation, and that happens exponentially. So this is what you see. Look at this picture very carefully. The first, so the pulse is applied, and this is what happens. You have, so here we have pictured 5 nuclei of same sample. एक ही सैंपल में कई सारे न्यूक्लियस हैं, तो मान लो कि मेथनॉल का ही 5 मॉलिक्यूल है, सब में एक न्यूक्लियस को हम देखें तो सबका स्पिन ऐसे ऐसे अरेंज्ड है. So you can see that how the spins are arranged pointing up. So pointing up, upward cone, You have so you see 1, this is alpha, this is also alpha, बीटा कौन कौन है, बीटा, बीटा, ये, सो बीटा स्टेट, ठीक है ना, 3 न्यूक्लियस, सो पॉपुलेशन ऑफ इनिशियली बीटा इज मोर, अल्फा इज लेस, राइट. This is the situation at time t. They are pointing in the downward direction. Then after, so this is when, so z component of magnetization vector, most, so 3 of the samples out of 5, 3 of them are having aligned in the, having the ms minus half as the component, the spin z component of the magnetization vector is pointing downwards, so beta state is more in number, alpha is less in population. Now after time t1, the time constant that we have defined, longitude, that is called longitudinal relaxation time, what happens, there is a kind of, so this alpha state was lower in energy, this is alpha spin state we have defined in case of like plus uh, half spin nucleus, alpha state like a proton, this is the lower energy and this is higher energy. So this is what already has happened when we have applied pulse and it has gone into this system after immediately. So this is immediately after application of pulse, this is the situation. Now once the pulse is removed after time, when you are observing after time t1, the situation will change. There will be a tendency to go back to the alpha state if it is the lower energy state, and so you will see that this alpha state has so population of alpha will gradually increase, and that is why you are seeing that signal, decaying signal. Okay, so this is one part. So now you see after t plus t1, that means after time t1, which we have put here, what happens, now it is going back to the alpha state, the sum of the spins are relaxing back, they are going back, so you have now more of alpha. So see, alpha, alpha, this is also alpha, this is also, so 3 are now, so 3 of them are alpha, so out of 5, 3 alpha and 2 beta. Initially when the pulse, at the time of application of pulse, this is what happened, 2 alpha and 3 beta. So population has now changed. So this is the relaxation change in the z component of the spin, that what we are seeing, one which was having plus half earlier, minus half earlier, is now changing into plus half spin, plus half component of the uh, having the plus half as the z component of the thing. So alpha and beta states, the population is changing. So this is one type of relaxation that occurs, that is a clear change in the alpha state and beta state population. So this is the thermal equilibrium state, equilibrium with the surroundings. It has achieved equilibrium with the spins are now in equilibrium with the surroundings. Alpha is the more stable state normally, and so you have most of them in the alpha state. Of course you have not yet removed the b naught. B naught is still there, only then this alpha and beta have different energies. Only the pulse has been removed, and that t1 is indicating that part. So after time t1, this is what happens when you have, so so more of beta than alpha. This is what, so all, so this is what we have seen, spins are relaxing back towards their thermal equilibrium situation once the pulse is removed. This is what happens. So this is what we learned. After time t1 has elapsed, the Boltzmann distribution profile is, you can mm, you can obtain. So t1 is the time constant for the relaxation to this arrangement on the right hand side picture, and T1 L2 is the half life of the arrangement, half life of the this arrangement that immediately you obtain on application of the pulse, immediately on application of the pulse. So that is the kind of situation. So this was. Now what are the factors that can affect this T1, the relaxation time? This relaxation that we are discussing, that coming back to the thermal equilibrium situation, there is reverting back to the from beta state, which is the excited spin state. They are reverting back to the alpha spin state. So there is a more population uh, after they relax back the alpha state, which was of course lower in energy, so it should have greater population as compared to others. So this is also called lattice relaxation time. Why it is called spin lattice? Because it depends on the surroundings. Okay, so fluctuations, local things, local magnetic field is important when they are relaxing back from beta to alpha, or alpha to, sorry, beta to alpha transition. uh, so the liquid or the solid matrix in which these nuclei are embedded, ये जो न्यूक्लियस है, जो मैग्नेटिक न्यूक्लियस की हम बात कर रहे हैं, ये किसी लिक्विड सैंपल में अगर है, जैसे यूजुअली वी डू NMR in a liquid solvent or something, then the solvent molecules also are randomly moving, and they will affect this thing, overall magnetic field that is there, and relaxation will be affected. So T1 that we are talking about can have a effect. So we are talking about tumbling. This tumbling मतलब ऐसे लुढ़कता हुआ molecule, suppose just like a rolling ball from a top of a mountain. That is a tumbling motion, you can say. So tumbling motion, एक और पिक्चर होगा मैंने डाला है, एक मिनट कहाँ गया, हाँ, टम्बलिंग जो हम कह रहे हैं ना, सो टम्बलिंग ऐसा कुछ होगा कि उलट पुलट होता हुआ, सो नीचे जो आप एनिमेशन देख रहे हैं, सो दैट इज व्हाट वी मीन बाय टम्बलिंग ऑफ मॉलिक्यूल, टम्बलिंग ऑफ द सॉल्वेंट मॉलिक्यूल्स. सो उलट पुलट अपना हो रहा है, घूम रहा है रैंडमली, तो डायरेक्शन. सो दिस, लुक एट दिस थिंग. So this is your tumbling motion when we am. So this is the picture that should emerge when you are talking about tumbling. So I'm going back to the previous slide where I was there. Yeah, tumbling. Yeah. So this is what the graph is important. So variation of T1 with the this motion, tumbling motion, if it is fast or if it is slow, that will affect the relaxation time. So you can see if the rate of motion is very slow, very tumbling slow tumbling of the solvent molecules, fast fast tumbling of the uh, tumbling of solvents. So that's the fluid tumbling can arise from the tumbling. So these are the things that tumbling of the molecules will be will affect the thing. So if the molecular tumbling is too slow or too fast compared to the resonance frequency, then so these are the two extreme situations: tumbling too slow, tumbling too slow. Okay, so tumbling too fast. So these are two extreme situations that we are seeing here. Looking at the curve for T1, this T1 curve जो ऐसे जा रहा है, so दोनों ही केस में जो रिलैक्सेशन टाइम है वो बड़ा हो जाता है. तो टम्बलिंग टू स्लो का मतलब सॉल्वेंट इज विस्कस, हाईली विस्कस So high viscosity of the solvent will lead to the ये जो molecule है which is we are observing, sorry, the molecule that we are observing which has this magnetically active nuclei, so it is not able to move freely, it is not then the time of relaxation will be uh, large. So relaxation time t1 is large in that case. So because or if it is too fast, if it is tumbling too fast, very low viscosity, then also it may happen that the relaxation time will be too high. So relaxation time is high, is tumbling in both these cases. So high viscosity of the solvent, low viscosity, in both cases T1 is high. This is because the magnetic field fluctuates, uh, that is, and the fluctuation in the magnetic field is not matching with the resonant frequency, the applied field. So that case the relaxation is not is takes longer to relax. But if you look at the middle point here, when the rate of motion is somewhere intermediate, then the relaxation time is short. This change in state alpha beta to alpha जो relaxation है, so quickest you are having quickest, as per the graph, quickest relaxation, short, or you can say shortest t1, shortest t1 quickest. So very fast relaxation happens when the solvent is not too viscous, not too or if it is doesn't have such a low viscosity, so intermediate viscosity. So you can say in comparison to a highly viscous or very less viscous thing, intermediate viscosity is good. It relaxes the thing very fast. T1 is longer, and this is what we see here happening. So what we are talking about is that at this point the tumbling happens at around the resonant frequency. So this is the situation we are encountering at this particular point, and the magnetic field fluctuates. The frequency of fluctuation of magnetic field in that case would be able to induce the spin changes effectively, and T1 will be short. Uh, so that's what you can correlate. If you increase the temperature, then also, so just as we have discussed the viscosity, you can understand that tumbling motion can be increased by temperature also. If we are having the same solvent, and if we increase the temperature, if we reduce the temperature, the the effect will be similar with reducing viscosity of the solvent. So viscosity will change if we change the temperature. So both things can happen like this. Or if you are, so you can discuss it many ways, like changing the solvent and comparing the viscosity at same temperature, or keeping the solvent same and increasing or decreasing the temperature. In both ways T1 can change. Okay, so if you have the same solvent and you are increasing the temperature from say room temperature to high temperature somewhere, then the similar effect will be observed, because as you heat water or any other solvent, its molecule, the motion of the molecules increases, and so you will have a faster tumbling. You can expect the viscosity decreases solvent, so tumbling of the molecules will be much faster, that contains that magnetic nuclei, and so you can relaxation will be there. Now the second aspect of the spin relaxation, what we have just seen, that alpha and beta states are changing. Okay, so this is happening time scale t1 that we have defined here, in that time. Now second type of relaxation is different. ध्यान दीजिएगा, बीटा स्टेट, alpha state. So we have seen that after the relaxation, that in the previous discussion, after time t1, alpha population is more and beta. So this is, we are here. Now in this type of relaxation, what we are talking about is there is no change in alpha and beta population. But what is changing? Look very carefully. There was more of alpha state, so you have alpha, alpha, alpha. So you had three alpha. There are three nucleus in alpha state, three nuclei in alpha state. Now look at their z component. So the z component definitely plus half, but if we could have placed them on the cone in several different ways. Okay, so they are all aligned. See that this vertical line, what you are seeing here, all the three alpha states, they, when we are placing them on the cone, they are at the same position on the cone, right? It is they they will try. There will be a tendency. Probability is that they should have. They can be variously dispersed on the cone. All will have same plus half component, z component. So you can see the relaxation. So this alignment is changing. Now you can see this is going here. So there is no, it is still the alpha state, it is still having the z component same, but the placement on the upper cone has changed. ठीक है, सब अल्फा स्टेट में प्लस हाफ कंपोनेंट ही है, z कंपोनेंट तो सेम रहा, कोन पे कहीं पे भी रखो आप इस वेक्टर को, ये जो एंगुलर मोमेंटम वेक्टर है, इसको कहीं उस कोन पे रखोगे तो प्लस हाफ कंपोनेंट तो सेम होगा. So if we keep them aligned, this is not a happy situation. There must be a, if they fan out, so that's what we are talking about, fanning out. फैन में जैसे तीनों ब्लेड एक जगह इकट्ठा कर दिया आपने, उस तीनों को आप डिस्पर्स कर रहे हैं तीन डिफरेंट डायरेक्शन में, but they are still on the same cone. So the plus half is remains, it is still having the plus half component as the z along the z. So this is what we mean. So similar thing you can think of for beta, beta part, beta, beta. So alpha, alpha, alpha aligned, beta, 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 beta and beta, you are seeing them in the downward arrow, they are also aligned on this, they are placed on the cone at the same position. Now in this particular type of relaxation, what will happen, they will be still having the z component minus half, but they will be now uh, just not placed on the same position. They will be still on the same cone, downward pointing cone, but now they are, see, still this is beta, but placement. So what we are showing here, the placement on the cone, the vector. So what we are seeing, that placement on the cone, placement of the vector on the cone has changed, right? So this is a type of relaxation that we know as spin relaxation. This is spin relaxation, in which there is no change in the alpha and beta state. You have same population, but instead of initially, if they are thought to be aligned, all the spins are placed on the same position along the cone. All the spin angular momentum vectors were pointing in the same direction, were placed on the same position on the cone, they were aligned. Now they are uh, placed differently on the cone, on the same cone, so such that their z component is not changed. This is the spin relaxation. Alpha and beta state in the initial and final is same. So initial and final, you note that uh, alpha, alpha beta population, so sorry, alpha beta population, final alpha beta population. This is same, unchanged, but the vectors, individual spin angular momentum vectors are they are placed differently on the cone, or you can say they are now not aligned. They are not aligned. As in the previous picture, we are drawing a line to show that all alpha alpha alpha, they are along the same line, beta beta beta, they are also on the same line. Okay, so they are now fanning out, which is also desired from to have a more stable system. So this happens. This is what happens in the second type of relaxation, that is spin relaxation. Okay, and so all the there is a bunching. First picture, there is bunching together of the things, and after that's what happens then when you have immediately after. This is what happens after the 90-degree pulse. You apply the pulse and immediately this happens, and slowly after the pulse is removed, they will get back to the position like this. They will change their bunching is. So it is the orderly bunching of the spins is not a happy situation. So they will get back to equilibrium where all the spins were pointing randomly on the cone. They were placed on the cone, but the placement on the cone is random. Okay, so individual spins spread out until they are uniformly distributed. So there is randomization of the spin vectors on the cone. ठीक है, such that their z component remains unaffected. Okay, in this particular along this thing. So this is what we mean. This is what we uh, call as transverse relaxation time, T2. So 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 this is what we say transverse relaxation time, and this is given by this mathematical relationship. It is also having a exponential relationship. So earlier we have seen the y component was directly proportional to t by t1, small t by capital T1, and this is small t by T2. So only difference, that's what mathematically looking at it is this, that is the, so randomization of the spin directions. Okay, keeping their z component same, that is placement on the same cone but randomization on this cone. That's what we achieve. And this is this is different from spin's lattice relaxation, the previous one. hmm. So that was the spin that we were talking about. Okay, so myt, so bunching of spins. So transverse relaxation time uh, is the time. So spins, so to become randomized, this is the time taken to randomize the spins. Previous T1 was the time to change the population from beta to alpha. So change in alpha beta population, that was T1. And randomization of the spins, the way we have talked about, aligned then not aligned. So this is the situation, that this randomization of the spin, this is time T2, transverse relaxation time. Okay, so it is the disorderly arrangement that we want to achieve, that the system wants to achieve for the spins. Okay, So the population of states remains same. I already told you. Only the relative spins have relaxing. T2 is the time constant for arrangement, and T2 ln2 is the half life of the this thing. So half life of this particular state is T1 T2 ln2, arrangement of the left side. So this is also called spin relaxation time, transverse relaxation time. Both mean the same. Uh, uh, so anything. So this is important part. So it is also to remember T2 is almost always less as compared to T1. So T2 is always less because it's simple. You can also imagine this is a, you don't have to do much effort. It is just fanning out of the, it is just a randomization of the spins that you need to achieve. So T1 is longer, T2 is shorter, or sometimes it may be equal. Okay, most of the time it is less. ठीक है, so local magnetic field can also influence this. So fluctuations are slow. Each molecule so local magnetic fields will affect the spin relaxation. If if the molecules are able to move rapidly in the from one magnetic environment to another, then the field averages to zero, and spin relaxation. So if you have so this is the situation. Local magnetic field. So if the molecules are moving rapidly, uh, okay, fluctuations. So there are 2 points that, yes, 2 points to make here. When the fluctuations in magnetic field is slow, molecules will be in their local magnetic environment. So each molecule will stick to the local magnetic environment. They will be there. That will be there present, and spin orientation randomized quickly around the applied magnetic field direction. So if the molecules if the fluctuation is not slow, molecules are moving rapidly, then there will be bunching of the spins for longer times, and spin relaxation takes longer. So that is what we see here in the I don't know why this happens. Full screen, sorry. Yeah, so looking at, so this picture tells you the thing. So when T2 is, so you see here T2, uh, T2 was this randomization of spin part that we were discussing. So effect of the molecular motion that we were talking about, how it affects. So relaxation is here. There's, if there's bunching of spins, it takes longer to do. So that's happening here. And when there is fluctuations are more, uh, magnetic field fluctuation is more, then the time scale is short. So this is the graph that we were getting. So in other words, molecular motion corresponds to slow molecular motion corresponds to shorter T2, and fast motion corresponds to longer T2, as shown in the picture. In the sorry. So from the graph, just a moment. Oops, where we are, yeah. So at, we also see that at very high viscosity at this point, the two are equal. T1 and T2 become equal. So from the graph also you are learning this way, that so you can see from the graph also. Okay, sorry. So here you can clearly see that T1 and T2 equal, become equal. T1 and T2 here are quite different. So when the molecular motion is fast, they are almost equal. All these points represent that they are becoming equal. So difference lies initially, and when the molecular motion is slow, T1 is fast, T2 is slow. But as the molecular motion increases, T1 and T2, the difference between T1 and T2 decreases, and finally, after almost at a intermediate situation in the middle of this graph, you see that they have become almost equal, T1 and T2, and that trend continues further. So it is the local magnetic field, and so these things can be calculated from the width of the NMR spectrum. So the decrease, this T2 component is evaluated by measuring this uh, full width, what we call as that width of the peak, full width at half maximum. This is also called full width at half maximum, we, or in short FWHM of the peak, of the peak. FWHM, this is, so anytime if you have to describe width of the peak, whether it's NMR, whether it is absorption, fluorescence, you always refer to FWHM, full width at half maximum. So this is the maximum, peak represents max, this is half maximum, and width, full width, you are taking the full width. So this is the full width at half maximum. So this tells you, so this full width is actually equal to this, so 1 by T2 pi T2. So the relaxation time, the spin relaxation time, can be evaluated by measuring this width at full width at half maximum. Okay, so this is typically line widths are around, so proton NMR, when they are conducted, it is T2 is on order of seconds, and line widths are around 0.1 hertz. And uh, so all our discussions are based so far in that magnet is perfect, and differences arise solely from the interactions of this magnetic nuclei with with each other. So sometimes there are also the magnet is not always perfect, and there could be something like that, field is different at different locations within the compartment, sample compartment, and so inhomogeneity does arises, and there is a line broadening due to inhomogeneous line broadening due to that factor also. So 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 inhomogeneous broadening is also there due to this instrumental factors. What we have calculated is the width that we have calculated, so we have to adjust sometimes for that factor, instrumental factor, and then calculation is more realistic, what you want to measure the relaxation time. So that is why we have to define this term now as a effective transverse relaxation time. So directly calculating with the width, it also includes the width due to the instrumental factors that may have to be taken into account, and some you can that can be taken care of by some uh, again the processing of the signal and adjusting to that, while including the Lorentzian shape, Lorentzian fitting profile. So that's something that we can do. So measurement of T. So T2 we talked about how we can measure, but T2 T1 is even slightly. It is slightly difficult to measure T1, and you have to apply two pulses, 180-degree pulse, then 90-degree, followed by a 90-degree pulse. And so this is can be done. First, apply a 180-degree pulse, so you achieve a complete reversal of the magnetization. So magnetization initially was pointing like this, now it will be pointing like this, and then allow it to decay. And after, as soon as once that decay has happened, you apply 90-degree pulse and then get it. So this kind of relaxation profile processes through 180, points to the minus z direction. So there is no component. So once you are at this stage, there is no component in the xy plane, and there is nothing that can be detected. So you apply again a 90-degree pulse to get something. Magnetization vector first shrinks exponentially and then falls through zero. That's what we have seen. Uh, okay, so this part we can T1 we can it will take longer to discuss. I think a little bit more on this we will discuss sometimes. Uh, yeah, so it is around 8 o'clock. I have to leave. So thank you very much for being attending the class in the morning. Thank you. And so we will discuss T1 part is slightly yeah, it involves two pulses. It is slightly complicated. We will talk about it later. And then one more thing I wanted to discuss, so that is for inorganic samples, compounds. You have also this NMR fluctuations, NMR signals in trigonal bipyramidal complexes or something like that. That will be interesting. Yeah, I will follow up in the next class. So stop.